Unfortunately, the sun was out a little while ago and now it's not. So when the sun was out, I went out and did a little data collecting, but we'll talk about that in a second. Because you have a little solar lab, you have a lot to do. It's not hard stuff, so, but I want to go through it. A few things are carryover from this week that we lost. Can you see this? No. We lost week 2. We didn't do a lot of online stuff. So a little bit of catch up, not too bad. But if you haven't got anything done, just catch it up this week. So like the 3rd hour of the movie, that's also listed. We're gonna do a little solar lab. There's the Patagonia movie. I moved that over to this week from last week. So if you've already watched it, you're pretty set. But there's kind of a laundry list of things here that I'll just go through today. You have kind of an electricity wrap-up assignment. In the submission areas, I've lined them up and labeled them all week 4. So week 4, Patagonia movie, watch it. Here's the questions, post up. The electric assignment, the solar lab, and then we're gonna start the individual project.
Is the electric assignment the electric movie?
Nope. That I think I left in week 3. Yeah,
Okay.
right here. Yeah. And I put a new link up. So if that was glitching on you, I put a new link up that should work for the 3rd hour. But again, this is just to summarize. There's no questions. So you should be able to do that fairly quick. So I just want to show you the submission area. I have a lot of week 4s. They're all due at the end of the week. So the calendar is going to explode. But, all right, I can fix it. Every time I go in, I have to fix it. So I have it all listed here, but everything's due Friday, so you have time to get it all done. We'll talk about the individual project. You just have to put together a proposal, simple proposal. This is lecture. The solar lab we'll do together in class, but I'll talk our way through it for everyone who's picking it up online. And then the Patagonia movie, I moved that link to this week and to today. So it is here. So it's just a movie about Patagonia and how Chenard transitioned that company to a sustainable company, kind of at the next level. It is probably the most sustainable company on the planet. Expensive stuff, you pay for it, but they have some really cool concepts as far as life cycle analysis, life cycle assessment, and life cycle clothing. So when you buy Patagonia, you're buying a lifelong garment. I don't know if you're aware of that, but they will repair it at any time for free. And if it ever completely wears out, they will replace it. Now, do we all want to use the same coat for the next 35, 50 years? Who knows, right? But if you are super sustainable, you would be like, yeah, I just want one coat. That's it. And you'd pay for it. All right, let me talk through the rest of this stuff here. This is an assignment that I want you to do and focus on where you live. So that may be a house, that may be an apartment, that may be a motorhome, I don't know, wherever it is. I want you to try to estimate how much energy is being used per month. Now, you probably all get an electric bill, maybe you don't see it, and that's fine. Hopefully you don't see it, so you don't have any idea how many kilowatts you're using, right? If you do see it, then you kind of know your target, but you're not going to get to that target because I'm just having you do the largest consumers of electricity in your home, such as a cook stove, often 3,000 watts. And you might have to Google this stuff. If you want to Google the model of cook stove that you have, you can do that and you'll get the wattage. Okay. So for example, a cook stove, 3,000 watts, maybe it runs an hour a day, maybe more at your house, maybe less. You estimate, right? So if it did run an hour a day, every day for 30 days, we'd be looking at 3,000 watts times 1 hour for 30 days, 90,000 watts. Okay. In Oregon, we pay anywhere from 9 cents a kilowatt hour to 13, 15 cents a kilowatt hour, depending on your region. And whether you click the little box that said green, I want to be green, that's more expensive. Yeah, anyway, so what you're gonna do is you're gonna total up these watt hours. And remember, a kilowatt is 1,000 watts. So if you're getting 90,000 watt hours, you got to get that to kilowatt hours before you can come up with like a bill, right? A water heater, that might run 2 hours a day. It might run more if you had 5 people on that water heater. Everyone's taking a shower. It's trying to keep that water temperature hot. It might run more. Again, you're just estimating approximately what you think it's doing. A lot of them are 4,500 watts. Some of the fancy ones are higher. Some of the older ones are lower. You could actually look at your water heater and see. Throw it hours a day times, we're just gonna use 30 for a month, not 31 or 29. And then come up with the watt hours. So you're gonna try and total these big consumers up. Right? Then you're gonna like try to calculate the total like billing. And then if you can find your power bill, let's make a comparison. So I think right now, I think we're 15 cents. Let's see, state of Oregon. Let's see if we can get a number. 50. That's what they're saying. So 15 cents on average. It's like it's as high as 19 cents, depending on your region and also what things you clicked on your bill per kilowatt hour. Okay, and if you find your electric bill, it'll say how many kilowatt hours you consumed last month and the billing, right?
So
Yeah.
we're going through calculating lights, every
You don't have to do
appliance.
lights. Lights are not a big consumer.
Okay, so just like.
Water heater,
water
stove, fridge, the big
heater, washer,
things.
dryer.
Yep. Yep, dryer, washer, not a big deal, but it is using your hot water, which
Yeah.
most of us have electric hot water heater. So yeah, that can be a consumer.
Oh, what if we have gas?
If you have gas, then it's not electrical. It's a
So my
different
stove
cost.
won't count, my water heater won't count.
Yep. You have a gas water heater?
I'm pretty sure. Yeah.
Yeah, check that, man. Those are bank.
We got
Those
a
are,
gas
they're
fireplace.
super expensive, but they're super efficient. Like to buy a gas water heater,
Uh-huh.
it's like $2,000.
Well, I'm gonna have, this is my old house. I'm gonna have to calculate my old house because I'm.
That's
between
fine.
houses right now. So.
Absolutely.
But
Yep.
I'm pretty sure it's a gas one. Everything, I mean, there's a gas fireplace, the stove.
Yeah.
gas.
No, if you had gas to the house, that makes sense. It's just the water heater cost
Yeah,
is expensive.
it's got pipes around it that look like gas.
No. Because everyone's gonna have everyone's gonna have different. I mean, the basic stuff, right? Water heater, your range, your furnace, if you're an electric furnace, then those are the big things, right? Fridge, freezer, those are all consumers. Microwave, but how often do you use your microwave? Like, if you're cook,
Is it a big consumer?
oh, it's huge.
Oh,
Microwave
mine's
and
running.
toaster is 1,500 watts. But we run our toaster for like, what, 30 seconds, right? And same with the microwave, we don't use it a lot. Those are the things that bury generators, like if you have a generator for your home. And it's on the edge and you like pop toast in and then start your microwave, that'll just pop every circuit of your generator. Cause they're so huge. Microwaves are like 2,500 watts. Yeah,
I really thought about it.
if you have wall heaters, those are big consumers, like any kind of wall heater. Right, if you don't have central furnace. A central furnace is a consumer, but if you don't have that, then you have wall heaters that are running during the day. Those are like 1,500 watts each. And those run a lot typically, not just an hour, if you want to keep a room warm. In the winter, right? And we're thinking now, although it's not very cold out, but we're thinking now, so. Yeah. Oops, let's not go there yet. Where was I? Oh, I was here. Okay. So, yeah, total the kilowatt hours. And this is 7 cents. I should update that. 7 cents is pretty damn cheap. Oh, I can't do it. Here. So let's use 15 cents.
So basically all we have to do is look up the appliance, figure out what its
Yep.
kilowatts are, and then
Estimate the time that it runs, because it doesn't run 24/7, right? We're gonna use 15 cents a kilowatt hour. And estimated an hour is not minutes, because you're gonna get charged per kilowatt hour. So some of the cheapest electricity in the country is right here. That's because, yep, Bonneville. Exactly right. All right. I should say 24. Dang. This isn't even a copy and paste. All right. So do the calcs and then compare it to your power bill.
Say you couldn't find exactly the same model, but like someone.
You're estimating time. I mean, the only way to get this exact is if you had, they sell these little meters you can put on circuitry. And it'll draw it exact times that it draws down, so. I mean, you're just estimating.
one of those radiator style water heaters. The
Yeah.
girlfriend was convinced it was sucking a lot of power, and I looked it up, and it said it was the most efficient.
Yeah, those are
heating you can
low,
do.
those
Yeah.
are low
Like,
wattage.
this is
No.
like cheap heat.
They just don't put out much heat.
Right, yeah.
You
I'm trying to
gotta,
heat my garage.
you gotta sit on top of them to
Yeah.
get heat off them,
Yeah,
but they're super efficient.
yeah.
So efficiency is, it's something you have to be suspect of, because the wall heaters that are like in the wall, those are almost 100% efficient. Which means all of the energy going to the heater turns into heat and comes into the room.
That
That's
doesn't
a,
mean it's not sucking.
it doesn't mean it's not costing you a crap load.
So the
They're
radiator.
very
could be-
expensive.
Could be expensive.
The radiator ones?
The radiator heater that I
Yeah,
have, that
yeah.
could be sucking a lot of power.
Absolutely.
It's just efficient in
Yep.
that it's all becoming.
That's exactly right. So the efficiency of a propane furnace or propane heat is lower because you have exhaust heat that goes out of the house, right? Electricity doesn't have that. All of the energy going to that electrical heater, all the heat goes in, there's no exhaust, right? So efficiency is kind of, it's suspect because just because it's high efficiency doesn't mean it's good.
It's just bang for
Right.
your buck.
Propane heat's way better than electric heat. Way better because propane has so much more energy in it than electricity does coming in. Electricity's got to convert it to heat and then a fan's got to blow it around, right? It's 100% efficient, but it's not very cost effective at all. So there's a lot of little like catches to all the advertising. All right, let's go through the rest of this stuff. Patagonia, you're gonna watch that, you're gonna post up. This you can't see, this you can't see, this you can see. This is called the solar angle calculator. And you're gonna use that today, and it looks like this when you click on it. Okay, so I want to go through this. This is super, we're moving into solar. So one of the first things we talk about is just the sun's rays and how to capture that energy. So I'll go through a little PowerPoint in a second. But this thing will give us solar angles. So we want to know, here, I'll click on the altitude angle. These are nice because they're all hot links and they'll explain what they are kind of in easier terms than just trying to know, like, what's the azimuth angle? I don't know. It's just a specific angle that is from south, right, on the compass rose. Has nothing to do with the angle up to the sun, but it's like the position of where you are from south or north. So the altitude angle is from horizontal up to where the sun's rays are coming down. That's important for solar because we want to position our panels perpendicular to the sun at a specific time of year, whether that's summer for maximum production or winter for minimum production, because that angle is very low in the winter, it's very high in the summer, or somewhere in between. An average, right? But we want to like design it up and know what angle to put that panel on, so it's perpendicular to the sun's rays. So the first thing we have to learn is, well, what angle is that? And you can get it with this any time of the year, any day, anytime, any location. It's super handy. So we'll do that for here in a second. Actually, I think I did that for you, right? That's our zip. So it's a rough, if you just put the zip in, you don't have the exact latitude, longitude, then it's roughly our area. Right? But if we had a device to give us latitude, longitude, which you can usually get from Google for a specific location, you can input that and have an exact spot, like your roof of your home type of thing. All right. So that's what that is. Let's go back. This is just, I'll refer to this. This is Prineville. And you can get different pieces of information on different locations. So I just extracted this and downloaded it. And we'll use it at another time. But latitude, longitude, a specific location, year, this was 2019, month, January, day, every day. And then this is like the solar information for Prineville, Oregon. So when you're doing solar design, you want to know like how many solar days do they get per month, right? In January, which would be like designing for the worst weather. Summer, they're going to get like 31 days of sun, right? For several months in the summer. So most of the design that goes on is in the winter. That's why this is January. Anyway, I just wanted you to see the data. We'll use it later, not this week.
Do the solar panels pick up anything with cloud cover? Because they tell you that you
Oh,
can
no.
still get sunburn.
Oh,
in
you will
cloud,
definitely get,
so-
you'll get good, there's decent production out there today. And it's not direct sun. It's not 100%. So if your panel's rated at 280 watts, you're probably getting 180 out there today, but you're getting something. Yeah. So that's what that is. Well, let me back up. Yeah. This is my PowerPoint, and this is your lab that we were supposed to do if the sun comes out. So I'm just gonna keep watching. The sun comes out. It's close to coming out. I just went out there and
Is that the fan thing right there?
no.
Oh.
No. So what you're gonna do in your lab, and if it never comes out, I collected the data, I'll just share the data with you. Is you're supposed to go out with something that you know the length of. So I have these, they're 36 inches long, right? This one's 42, 65 long. You set it on the ground in the sunshine, hold it vertical, and it makes a shadow. You measure the shadow. You know this length, you do trigonometry, and you have the angle of the sun's rays coming to Earth at that time. So you also document the time, right? You come in and do the trigonometry and you have your angles at a specific time. So very rude, simple thing, but it gives you this, right? It gives you the angle that the sun's coming in. In the winter, it's low. We have low angles because the sun's low in the sky in the south. In the summer, we have high angles. It's up high. And then somewhere in between, which is March 21 or September 21, that's our half quarter year spots. It's somewhere in between. So the solar panel can be placed for a winter pickup, which is very efficient in the winter and not very efficient in the summer, or somewhere in between, like the mid pickup or a summer pickup, which would be like a maximum production.
Do they ever adjust?
Yeah, there's trackers, a big arrays track, but not typically on residentials. Residentials are fixed. I have 5 panels in Prineville and I just put a 3-position bracket on it. So
Right, that's
I
what I'm
can
thinking. If you-
manually just adjust my panels in Prineville. So when I go over in the winter, I have them super steep because the sun, like, I swear, it barely comes over the horizon this time of year. And it picks up really good.
Bigger ones, they just like rotate off.
Yep. Yeah, there's a big array in Sandy that's all adjustable array. So in the morning, it's like straight up and down, waiting for the sun. And then as the sun comes up, it tracks. But keep in mind, tracking would require what?
Power.
Power, yeah, so you're less efficient, but it's more efficient in collection, right? So there's a balance there. You see some tracking big arrays, and then you see some big arrays that are fixed, like they're just not gonna track. The other thing is on all the tracking, especially the one in Sandy, which you can see from 26, so if you keep your eyes open, you'll see it on, it's not far out of Sandy. On any given day, there will be a whole row that's just not tracked, like they're all pointing up and one row is just like straight up and down. And that's because the tracking motors have gone down or something broke, or there's a sensor that went out. So I'm sure it's a continual battle to keep those things tracking. Yeah, I don't know the whole efficiencies of it. All right, so let's talk about this because you are gonna do this. You're gonna use my data. I mean, if the sun comes out this week, you should do it because it's kind of fun. But what you're gonna do is hold something vertical that you know the length of. And what I did is went out with this, the longer stick, stuck it in the air, and then just used the tape measure to measure the shadow. So the thing that I stuck up into the air, vertical, was 42.625 inches long, right? And then I took a tape measure and measured the shadow. And it was 101 inches. So if you've had trigonometry, you know how to calculate this angle. I'll call it alpha. Using the opposite side and the adjacent side, what trig function is that? Tangent. You could use Pythagorean theorem to get the length, but we want the angle.
We need the angle.
Yeah, we want the angle. Yeah, because really what we're gonna do at some point is we're gonna place a solar panel perpendicular to the angle, right? We want the solar panel flat to the sun's rays. All right, so it's tangent. So tangent of that angle is equal to the opposite 42.625 inches over the adjacent 101 inches. If you don't know trigonometry, that is okay, because really, this is the only thing we'll ever probably do with trig in this class. But to get alpha, we have to take the inverse tangent of both sides, which clears this, and then alpha equals tangent minus 1, 42.625 inches over 101. Again, if you don't know trig, that's okay. To get this angle, it's going to be that divided by that, and then take the inverse tangent of it. On my calculator, I have tangent, and then I have what's called arctangent. Tangent and arctangent. So on an HP, it's a little different. You can find it on your TI, I'm sure. 42.625. So on an HP, you enter the number, and then you take the next number and you just divide it. So it ends up to be that. And then I'll run this blue arctangent. 22.88 degrees. I did it at 11 a.m. on January, what's today? 29th. So every day it changes. The solar angle changes every day. Very little, but every day. And then the location was MHCC, and I just put in 97030 for the zip code. Right? So that's kind of everything you'd want to collect. So if you do this at home, I don't know, I feel like offering extra credit if the sun comes out and you do it. I'll give you extra credit. So you need a device that you know the length of. So that's the first thing, right? And then you got to measure the shadow, record the time, know the day you did it, right? and your location. Because we want to compare it to the calculator. So 22.88 degrees. That's what I got. My little experiment. It was rough to measure this shadow. It was like, it was a little fuzzy. It was pretty direct sunlight, but it wasn't crystal clear.
So flat.
Yeah, it's got to be flat, and you got to hold your stick vertical. So I had a little bullet level on there, trying to hold it vertical. I mean, it's an experiment. They actually have devices, right, that are perpendicular for this exact thing. So if you have a solar company come out to estimate the possible production, they'll probably use the calculator, but they might come out and actually do a test because you want to look for shadows too. You can't have trees and buildings and things that are going to be in the way. So, all right. So that's what I did with that. And then I went here and input. Here, I'll start. Oh. So you can see how that works. Oh, that's the one. We'll do that one in a bit. All right, so it comes like this, blank. So again, if you know your exact latitude, longitude, you can put that in. If you don't, you can put in a zip code and then say look up right there. And it does. So it looked up this, right? But I think Google Maps, doesn't Google Maps do it? Like,
I think you could like drop it.
yeah, that's what I thought. It's our lovely college.
Or you could at least search things like.
We're in this wing. We're like right here. I know you can do this.
Maybe Google how to do it.
Yeah, maybe Google how to do it. I thought you could get it like just a quick button, would give you lat and long. Anyway, if you know the exact latitude, longitude, you can just input it. You see it there? No. Tips and tricks missing. I know you can do it. I just don't remember how. Anyway, all right. Or you can just use there, right? So that's going to be pretty close. What is the day? It's the 29th. It's not 2021. 2024. Elevation I did estimate. And again, any of these you can click on.
And
And
it'll
it'll
just Google your current elevation, I'll tell you.
give it to me. My guess was 150. Which is,
321 feet.
oh, it's more than I thought.
That's according to my phone.
Oh,
Use
let's
this.
go with it. Time,
Meters.
feet? No,
Oh.
that was in meters. That's a good catch. Sorry. 11 a.m. is when I did it. That's the correct time zone. Clock time, not solar time. Daylight savings, no. And this is if you click on it again, you'll see that this has to do with your rotation from north or south. Doesn't really matter for what we're doing. All right, calculate. And then it fills it in. So it's coming up with an altitude angle of, remember, this is the altitude angle. That's what I calculated. 2386, what did we come up with? 2288. So we are 1 degree off the calculator, which from my rough experiment out there, I was pretty happy with. Like, that's pretty close. That could be like my ½ inch measurement of the shadow wrong, right? So
Does that affect like how efficient it is? If it's like off.
1 degree isn't gonna do much. Yeah, because the sun's continually moving, right? So it probably moves 1 degree. I mean, you can probably Google this, but I bet it moves 1 degree in 5 minutes. So not really. I have a slide on production of a panel and you'll see kind of there's a range And there's only one spot where it's 100%, and that's when it's perpendicular. So that's the other deceiving part, is when you're buying solar panels, you're like, oh, this is a 280 watt panel. Yes, you're gonna get that 280 watts for like an hour at the most,
Unless you're consistently.
unless you're moving with it, tracking, yeah.
I have an
Yep.
RV with a solar panel, some solar panel on the top, and like right now. If I leave it on and I just run the fridge.
Yeah.
Like low, it doesn't even charge.
Yeah.
At all.
No. Nope, it won't. All right, so there you go. That's kind of all we want. There's more information down here. But that's how we're using the calculator for now, just to compare our angles. And then when we do our design, because at the end of the term, we do kind of a fun design, you can use this to place your sustainable home anywhere you want. So if you want to build it in Bend, or if you want to build it in the Wallowas up in the woods, you just got to know the latitude, longitude, and you can get the sun's rays and information to do the calculations. So, all right, cool. That's the lab. That's this solar lab thing, this thing. So,
It's being more efficient, like using nuclear, because it's always like getting, that's.
it depends, yes, in general. I mean, they have a lot more what we call solar days than we have. Yeah, and they have a more consistent solar angle, right? It's just always there. So we're at the 45th parallel. It's not perfect for solar, but it's very effective.
Even when you're, say it's winter, sun's real low.
Yep.
And you have the solar panel pointed directly, it's perpendicular to the sun. It's still gonna be less than,
No, that'll
Oh,
be
really?
good production. Yeah,
so even if it's during the summer and the sun's right
Yep.
above it, isn't
Yeah,
it
it's not-
closer? Is the sun close, cause
it
close,
doesn't matter. We still get the same amount of energy whether the sun's far away or close,
okay,
because there's no resistance. Outer space, there's no resistance
Oh,
as
yeah.
far as the energy that it's sending.
oh, yeah,
So distance doesn't really matter.
Okay.
But perpendicular matters probably the
In the
most.
winter, we're closer to the sun.
We're just off at an angle.
Yeah.
oh, that's why it's like summer.
Yeah.
Yeah.
Exactly. All right, cool. Let's go through this little, we only get an hour. Let's talk about the individual project, because I want you to propose this by Friday. And we can just talk our way through it. So. Reduce or produce, either one, you can choose. If you're gonna reduce, then you just choose a resource that you'd like to try to reduce. So if you're gonna choose like water, you're gonna wanna use less water, or waste, you want less garbage. You kind of have to get buy-in from other people that you live with to try to make that kind of adjustment. It's hard to do. You could reduce, consumption of fossil fuel. You could reduce consumption of products. You could reduce, you can choose anything you want to reduce. There's all kinds of resources that you can choose. That's a fun one in that it just makes you like change your habit, right? We have to change something for 6 weeks, basically. So the important thing for reduction is that we have some kind of baseline, that we understand what we're currently doing, what kind of change we want to make, and then document the change and also measure. So if you have a water bill and you want to do water, that's pretty easy, because water bill is going to give you consumption. How much water you use, you're being charged, right, per gallon on your water bill. So that's one thing that's pretty easily quantifiable, right? If you want to do trash, then you need to do a couple weeks of measuring trash. So you have your baseline and then make the adjustment, whatever kind of adjustment you're trying to make, right? If you currently drive to school and you want to like reduce your petroleum consumption, then you need to keep driving to school for a couple weeks and document, like write down how much fuel it's taking to get to school, right? Then make the change and then document the new consumption. Does that make sense? So some of these we have to have a baseline for and then make the change and then collect new data. I'm good with all of that. All of those kinds have been done before and you can do it pretty simply and successfully. The production is you gotta make energy somehow. So that one's kind of fun too, right? Lots of different ways to make energy. You can put together a solar system. I actually have solar cells. You have to do a little bit of soldering and a little tinkering. But that's kind of fun. I have a big solar panel in the back. But then we've also had many wind turbines made in this class. They're also fun to do. Little DIY, do it yourself, wind turbines. I've had hydro systems,
How fast does it need to go?
depends on your generator. Yeah, depends on your generator and how efficient of a system you can put together, like how smooth it is. The one on the table needs a lot. It's gotta have a big startup to get it spinning, and then it'll spin kind of down in the 15 mile an hour range. It spins just fine. But it takes a solid 30 to get it going, unless you just hit it with your hand to start it, and then it'll go. So it's all about the efficiency of that bearing and that whole setup, but it's pretty fun to do. I've had bike generators where you just stick a generator on a bicycle and you sit on it and pedal. You can produce easy that way. I have a number of different generator sizes, so you don't have to buy anything. I have small generators like in the little wind turbines. I have a couple bigger ones that were like on bike generators that we've gotten in the past. We've had hydro ones. We've had people try to create energy out of the rainwater. So capturing rainwater and then dropping it down a gutter. Can we produce anything from that? So those have been pretty fun. You don't produce much, I'll let you know. Because currently it's not raining, so that would not be producing. But yeah, either one, reduction or production, you decide. This is just a proposal. Hey, this is what I'm thinking. If you're gonna do a reduction, I do want to know how you're gonna collect the baseline, kind of what the idea is for the change, and then collecting the new data. But that's it. But we need to get it going because we're running out of weeks.
How badly did week 2 screw you up?
Not too bad in here. We can adjust. There's no prerequisite following this course, like that we have to get through certain content. But everything I want to do, I don't know that's gonna fit, right? And the whole hybrid thing is a little odd. We only get an hour face to face. And then we're supposed to do a lot online kind of thing. So I don't know. This class is fun. All right, questions on this?
When do you want to close?
By the end of the week, 2/2, I think it says. Yeah, isn't that Friday? I think that's Friday.
Did we just post a picture of solar lab that we just kind of did it for us?
So this, yeah,
Post picture.
image is fine.
Okay.
Yep,
And then if we wanted to do the extra credit, then just post another one later.
yeah. So when the sun pops out, if you get outside and do a measurement and calculate a solar angle, that'd be cool. I'll put that up as an extra credit submission. All right, let's talk about solar real quick and then we'll be done. So this, I'm not gonna go into solar thermal, although solar thermal is super efficient and super cheap. So solar thermal is basically using the heat from the sun to heat water, right? And then that water can be circulated through the house as heat, or it could be circulated straight into your water heater and reduce the load of the water heater. So that's putting a heat exchanger on your roof that is think of like a heat exchanger in your car, right? That puts heat in the cab of the car. The heat's being generated from the engine. With the solar thermal, it's being generated from the sun. And even in the winter, you can collect a lot of heat from the sun if you have a thermal collector, right? It's like sitting in your car and the sun comes out and all of a sudden you're getting really hot because it's like baking in there, right? That's the same concept. So I'm not going to go into that. I'll stick with PV for now. So let's talk about what we get from the sun. This is important. The solar constant is the amount of energy that comes from the sun. It is 1.37 kilowatts per meter squared. Think about that. 1.37 kilowatts. A meter squared is this big. It's a little different than a yard, but about the same as a yard by yard or 3 foot by 3 foot. That is one heck of a lot of energy coming from the sun per square meter. 1.37 kilowatts. It's a lot. So that's the first thing. We round this down to 1 when we design. 1 kilowatt per meter squared. And that's because it's got to come through a number of things to get to us. This is like in outer space. So it's got to get through our atmosphere. Our atmosphere has a lot of dust and a lot of particles. Sometimes it has moisture that gets refracted away, right? So we use 1 kilowatt per meter squared.
Like the ISS, they're like probably super efficient up there.
Oh, yeah. Yeah, super efficient. Collecting a lot of that. The problem is our solar collectors are not that efficient, but what they get is more than what we get because they're on the outside of the atmosphere. So let's talk about watts. Like, what the heck is a watt? All right, so let's talk about it. Most of us can relate watts to light bulbs pretty easily. Like, you have a 60-watt light bulb, you have a 40-watt light bulb, or you have a 100-watt light bulb, right? So what does that mean? It's the rate of producing or consuming. So a watt is a rate. It's not, it is a per unit time thing. So 60 watts means that we are consuming 60 watts per hour. It's a watt hour. So even though they don't say that on any of the packaging, watts are in form of time. They're a consumption. So your 60-watt light bulb, that's for an hour. Right? If you turn it on, turn it off, that wasn't 60 watts. That was, you got some kind of illumination, right? But you didn't consume 60 watts. If you're leaving your lights on all day long, then yeah, you got 60 watts times 24 hours. Then you're consuming some wattage, right?
Is there a correlation between output and watts? Like how much light you're getting?
No, well, no,
There's a different measure of that, right?
yeah, lumens is the measure
Correct.
for how much light you're getting from something. But it's so dependent on these days, how that light's being generated. So like the old incandescent, 60 watts, right? Took a bunch of voltage and a bunch of current, and we didn't get that many lumens. I think I have a slide on. Yeah, this has lumens. So lumens is the amount of light you get, right? So here's a 60-watt incandescent. That's our old light bulb. They still sell these. They tried to eliminate them, but people resisted. You get 800 lumens from this thing, right? But it's using all 60 watts. For sure. Then we went to fluorescent. So those dropped from 60 to 13 watts. So a lot of savings there for about the same amount of lumens, right? So the same amount of light, 13 watts versus 60 watts. Fluorescents were a big jump. We saved a lot of energy with that move. And now we've gone to LEDs, right? And you can get these at different levels too, but this is similar to the fluorescent, but this has like kind of bad, nasty gases in it that are not real environmentally friendly. And that's
Well,
what,
it's not the gas, there's mercury.
yeah.
So like in 2027, they're like, they're internationally, they're gonna ban
Yeah,
mercury fluorescent tubing.
yep. So
And
that's,
it'll last.
that was the growth and the, yeah, how long it lasts is a big thing. So, I mean, look at the difference here, incandescent, fluorescent, and then LED. So, yeah. But lumens is the amount of light that we get. And the cost has changed and come down. This was very expensive in the beginning. Now the cost is coming down pretty quickly. So,
We're talking about that in that video. Like,
Yeah.
The guy was talking about how he was saying that because the video was 2012. he was saying, he's like, yeah, LED is really expensive right now. And I
Yep.
was like, oh, they are, and I looked it up, really cheap now.
Yep. All right, so just keep in mind watts, this rate of consuming, that there's a rate involved in it. So that's why, like, when you want to calculate your watts, you want to do that over time, right? If you did the lights in your house, you'd have to say, oh, I have all these 60-watt light bulbs, but these are only on so many hours a day, and these are only on so many hours a day. So we don't just multiply by 24, we try to figure out like how much they're running. I think there's a chart on this slide. Yeah, so here's, and this PowerPoint's up if you want to use it for some reference. Clothes dryer, 4,000. See, my eyes aren't that good. 4,856. And they're using 0.8 times, so 0.8 hours a day to kind of come up with their estimate of.
Does the current, like, matter that much at that scale? Like,
No,
whether it's-
no,
Right.
these are all gonna be alternating. I don't know what direct would be in.
Well, like the LED bulbs, isn't it like it's AC and then it converts it to DC, like LED?
Some of them did, and now a lot of them are just driven off of 120.
Really?
Yeah. There's been a lot of growth in those things, but in the beginning, they were, they had little converters in there, and then they 12 volt, and then the LED worked. So, oh, here's the 1 kilowatt per meter squared. All right, so I think I have I'm just gonna go through, oh, nope, no graph, that must be in the next slide on production. This is what they look like, right? Solar panels, we have one in the back, we'll look at it pretty closely. These individual rectangles are solar cells. So the cell is this, that's a solar cell. This is an array of cells, which is how panels are sold, right? So this is an array of cells. This is a polycrystalline. This is just one big crystal that they wire up different areas of. So the advantage to these things is you can take a rock shot to one of these and it'll take out a cell, but the other cells will still produce. So that's kind of why they did this, so they didn't end up with one of these amorphouses that if you get a rock into this, the whole panel's down. So we definitely have gone with solar cells, and an array of cells makes a panel. All right, and I have actual individual cells. And then we have an array in the back, which is a panel. They come in all sizes and shapes. Here's one. Weighs 22.9 pounds. It's a little 80-watt panel, right? Here's the dimensions. This was the price. I don't know when this was. These prices have gone up and down, never really stabilized.
So the 80-watt is saying how much power it can consume.
Maximum. Yeah,
Maximum.
so here's the information typically on the back of the panel, right? Typical power 80 watts. So that would be sun perpendicular to the panel. Right?
That's max it can produce.
Yep, maximum it can produce. Yep. This is a little panel. So this one, this is probably a 230 watt. But this guy, right? Only four cells wide. This one's 1, 2, 3, 4, 5, 6 cells wide and a lot longer kind of thing. So again, all kinds of information here. Low power output. So that's a pretty low current. Voltage 21, voltages in your homes like 120 volts. So they're pretty low voltage, low amperage. They don't have a lot of power, but they are supplying energy, right? They don't have any moving parts. Very beneficial. Literally just capturing sun, having some molecules jump around. That's what this slide's about. Sun comes in, activates some electrons, moves them from the positive to the negative side, boom, we have flow. Creates current. Right? Efficient, not so much. 16% efficient, 14%. I didn't put a percentage with this one. That means of the 1,000 kilowatts per meter squared coming, we're collecting 16%. It's horrible. It's about as good as we do. There are panels that collect like 40%, but they are like 10 times the price. So
What it is about. this
just
that they
better
collect so
crystal,
much.
better manufacturing of higher quality crystal organization, some different materials that are more activated, so. You know, the more the material is ready to jump, the more electricity it's gonna produce. But that's probably a rare material and harder to work with and all those kind of things.
Probably something more like industrial.
Yeah, so here's another panel set. This is a 4-pack of 265 waters. So $1,200 about, you know, for a 4-pack.
They're full.
Yeah. Yeah. So, and we're gonna get 4 times production, right? So we might get up to a kilowatt of decent production during the day. But
What
that's
is that
for, huh?
What is that pound, like 1,000?
So that's why you do the home thing. You'll get a feel for how many kilowatts, you'll be blown away by how many kilowatts you consume per month. It's a lot.
Yeah, I just got my electric bills.
Yeah, no, we're consumers of electricity, man. We just thrive on it. And then, you know, everything that we design seems like is a user. So, yeah, you'll get a feel for it. Here you go. On average in Portland, 1,000 kilowatts per month residential. That's just a very broad average. Right? Keep in mind, this is 1,000 watts possibility per hour or 1 kilowatt. So if we get a sunny day, we might get 5 hours of production, maybe 5 kilowatts, and we're looking for 1,000 per month. 4 is not gonna do it. So that's why you see substantial arrays on roofs, and that's still not doing it for that home, but it's offsetting, so we'll talk about that more as we get there. All right, we are pretty much out of time, but this is, we've already talked about, kind of just shows you a graphic of how this whole thing works. And that solar angle that we're trying to calculate, that's the lab, it's also in here, same as the one before. And that's the last slide, so we're good. All right, get all of those projects done. I will do an online thing Wednesday, so look for an online lecture Wednesday.
That's just the, like.
Yep. That's this thing. All right, thanks. Good job, everybody.